Welcome to The Explainer. Today, we're going to pull back the curtain on an incredible, invisible force, a force that powers pretty much everything in our modern world, from the phone in your hand to the entire grid that lights up our cities. Okay, so let's start with a couple of modern mysteries. Have you ever really thought about how an induction cooker heats up a pan with literally no flame? Or how a wireless charger can send power to your phone right through the air? I mean, it really does feel like magic, right? Well, it turns out it's not magic. It's physics, all thanks to a discovery from way back, almost 2 centuries ago, by the brilliant Michael Faraday. So to solve this magic trick, we first have to get our heads around an invisible ingredient. It's called magnetic flux. Now, I know that sounds a little technical, but stick with me, because once you get what this is, you'll see exactly how all this wireless power stuff actually works. All right, so what is magnetic flux? Let's use an analogy. Picture a magnetic field not as lines on a page, but as a steady downpour of invisible arrows. Now, imagine you're holding a hula hoop out in this rain. Magnetic flux is basically just a count of how many of those invisible arrows are passing through your hula hoop at any given moment. Simple, right? More arrows passing through means you've got a higher flux. Okay, so using that analogy, how could we get more arrows to go through our hula hoop? Well, there are 3 basic ways. First, you could make the rain of arrows heavier, right? That's like using a stronger magnet. Or you could just get a bigger hula hoop, a larger area. And finally, you could change the angle. You'd tilt that hoop so it's perfectly facing the rain, catching the absolute maximum number of arrows. So you've got strength, area, and angle. Each one is a key part of the equation. But here's the thing, and this is the part where it gets really interesting. Michael Faraday's big aha moment was realizing that just having magnetic flux, just having those arrows pass through the hoop, wasn't enough to do anything. The real magic, the breakthrough, happens when that flux starts to change. Think about it like this. A static, unchanging magnetic field is like a perfectly still, calm pond. Pretty, but not much is happening. But a changing field, that's like throwing a stone into the pond. It creates ripples. And it's in those ripples that we find the power. It really boils down to this incredibly simple but profound idea. If there's no change, you get no electricity. It's that black and white. But the instant that magnetic flux, the number of arrows passing through our loop, starts to either increase or decrease, boom, a voltage is created or induced in the wire. That is the absolute core of Faraday's law of induction. It's the one principle that honestly powers almost everything in our modern world. So how do we actually make it change? Well, remember those 3 factors we talked about? We just have to mess with one of them. We could change the field strength, maybe by moving a magnet closer to a coil of wire or pulling it away. We could change the area, making the coil bigger or smaller, or, and this is the one we use most often, we can just change the angle by rotating the coil inside the magnetic field. Any of those actions will change the magnetic flux, and that change is what generates the voltage. Okay, but it's not just that it changes. It's about how fast it changes. The speed of the change is everything. Think about a water wheel. If you have a slow, lazy trickle of water, the wheel is going to turn really slowly, right? But if you open the floodgates and get a powerful torrent, that wheel is going to spin like crazy. It's exactly the same principle here. The faster you change that magnetic flux, the more voltage you're going to generate. Speed is power. All right, but if you were paying close attention to that equation, you probably noticed a little negative sign hanging out in front. Now, that's not a typo. It's not just some weird math thing. That negative sign is actually pointing us toward a much deeper truth about how the universe works. It's a fundamental rule of opposition, and it's what keeps everything in balance. So why the negative sign? Well, it's all explained by something called Lenz's law. And what Lenz's law basically says is that nature always pushes back. It's this fundamental principle, and it has these huge implications for how we even think about energy. Here's a way to think about it. Let's say you take a magnet and you try to push it into a coil of wire. Well, the electricity you create in that coil is going to generate its own magnetic field. And that new field is going to push back against the magnet you're holding. It's literally nature's way of putting up a fight and saying, whoa, not so fast. And this pushback is absolutely crucial. Why? Because it means you can't get something for nothing. There's no free lunch in physics. That negative sign in the equation, that's the universe telling you that you have to do work. You have to expend energy to overcome that resistance. It's a really elegant, beautiful example of the conservation of energy in action. Nature always balances its books. Okay, so let's recap. we've got this idea of magnetic flux, we know that changing it is the key, and we know that nature pushes back. Now let's put all those pieces together and see how this one elegant law powers literally everything around us. So the way physicists think about this today is a little more abstract. We say that a changing magnetic field actually creates an electric field. It's kind of the same idea, just framed differently. But this concept, this link between changing magnetism and electricity, is the absolute foundation for how pretty much all our electrical technology works. And I mean it when I say it's everywhere. We're talking about the massive, colossal generators that light up entire cities, all the way down to the tiny little motor in your electric toothbrush. Faraday's law is at the heart of it all. It's in the transformers hanging on power poles, it's in your induction cooker, and it's even in the incredibly complex MRI machines that literally save lives.
Let's take a power generator. It sounds complex, but at its core, it's just a giant coil of wire that's being forced to spin inside a powerful magnetic field. And by constantly spinning, it's constantly changing the angle. Remember that? And that constant change in angle generates a steady stream of alternating current. That's it. That's the electricity that flows into your home.
Transformers are another really clever use of this law. What they do is use a changing electric current in one coil of wire to create a changing magnetic field. That changing magnetic field then expands out and talks to a second nearby coil, creating a brand new current in that one. There are no moving parts. It's like a game of magnetic telephone, and this is how we can easily step voltage up or down to manage our power grids super efficiently. And this brings us right back to where we started, to our modern magic. An induction cooker? It's just creating a really fast-changing magnetic field right under the glass. That field induces a current directly inside the metal of your pan, and that current is what makes it heat up. A wireless charger? It's doing the exact same thing, but instead of creating heat, the current it induces goes right into charging your phone's battery. See, it's all the same beautiful principle, just applied in different ways. So, think about that. Faraday took a completely invisible force, figured out its secret, that it has to change, and turned it into the engine of our entire civilization. It really makes you wonder, doesn't it? What other invisible forces are all around us, just waiting for someone to discover their secret? What new magic are we going to unlock in the next 100 years?